This assessment is one in a series of us taking the same molecule and doing a little bit more each time. At this point, the assessment is asking us simply to draw the spectrum, but only indicate the number of signals. It doesn't ask us to take into account splitting patterns. We're just kind of drawing how many signals would we expect to see. Now, if you look at the molecule, you'll notice we've got labeled A, B, C, D, and E. How many hydrogens give us A? Well, there are 3 methyl groups, and those 3 methyl groups, we have free rotation around the neighboring carbon-carbon bond, so those methyl groups are all identical, so we would expect signal A to integrate to 9. Signal B, that's a CH2, we would expect it to integrate to 2. The same is going to be true for the signal that corresponds to the hydrogens at C. That's also a CH2, so we would expect it to integrate to 2. D, there is only 1 hydrogen there, so we would expect it to integrate to 1. And then the 2 methyl groups at E are equivalent. So right now we've only got this one up here labeled as E, but this methyl group down here is equivalent. Boy, I really messed up pointing. This methyl group is equivalent based on free rotation. So E should integrate to 6. Later on, we'll talk about the multiplicity and the chemical shift and all of that. But for now, what we know is we can draw a spectrum with 5 signals that have these integral values. So let's put those on there. And again, this question points out, or in this assessment says, it doesn't matter about the chemical shift. We'll add to that when we work this same assessment later on. So let's just draw 5 signals. We'll draw the one for A being really tall because it integrates to 9. We'll draw the one for B being a little bit smaller because it integrates to 2. For C, a little smaller, or still the same size because it integrates to 2. D, a little bit smaller because it integrates to 1. And the one for E, we'll have it go up about halfway because it integrates to 6. And because we can't always trust our art, 1, 2, 3, 4, 5 signals, that's good. 1, 2, 3, 4, 5. We can't always trust our art. Let's write what it integrates to. Integrates to 9, integrates to 2, integrates to 2, integrates to 1, and integrates to 6. If we were to look at a spectrum of this molecule, we would expect to see 5 signals with these relative integral values. Disclaimer, they'd be at different chemical shifts, and eventually we're going to draw them as split peaks, doublets, singlets, triplets, etc., based on their neighbors. But for what we know now, 5 signals and there are integrals. We'll see this again. Stay tuned. Not so fast. I left too early. We were supposed to label the A, and I think we kind of put them in order, so hopefully it's obvious, but let's do what the assessment asked us to do. The one that integrated to 9, that was A. The one that integrated to 2 was B, C, D, and E. Again, I wrote them in this order, A, B, C, D, E, just because it was convenient. When we look at a real spectrum, they won't, but now we've got the assessment answered fully.